Okay, good morning, everybody. And today we're going to try complete our uh, discussion about special senses by talking about finishing off what we were saying about the eye, and then talking a little bit about the ear as well. So we finished off last time. We talked about some of the diseases that may affect the eye. I'm just going to briefly discuss with you some of the disorders. These are not diseases, these disorders of the eye and which result in disorders of sight, and very often due to slight imperfections in the structuring of the eye. So the commonest of these is the condition of myopia, and this may well be familiar to some of you because it's a very, very common disorder of the sight. And you'll remember that I told you before that the cornea is very, very important in the formation of an image. In fact, most of the focusing of the eye is accomplished by the cornea acting as a lens. To do so, it has to be perfectly shaped. And in the condition of myopia, the cornea is too steeply curved. And as a result, the image it forms, the focus of the image is ahead of the retina. The sharp image falls ahead of the retina, not on the retina itself. And what falls on the retina is in fact a blurred image, and this is especially true if the person is looking at something close by. So that is where the name short sight comes from. It's because they have difficulty focusing on things which are close by, and as the result of this, they suffer from blurred vision. There is another contributing factor, and that is that often the eyeball is too long. Instead of being perfectly spherical, the eyeball is slightly long, and that contributes to the fact that the image falls ahead of the eye, of the retina rather. Now, this condition is very easily corrected, and corrected by putting lenses in front of the eye, either glasses, such as I'm wearing, or else contact lenses will correct for this and will cause the image to fall neatly onto the fovea and the macula here at the back of the eye. So that is the condition of myopia. Now, I should tell you, there are increasing numbers of cases of myopia, especially in children. And it's something of a mystery as to why this should be. There are several suggestions. And one of them is that, in fact, a strange idea, but there seems to be a correlation between the amount of light that children sleep with and the condition of myopia. You'll know that in modern times, of course, we have a tremendous amount of light around us, especially at night. And there is some suggestion that children are being subjected to too much light while they are sleeping. And this has some effect on the development of the eye, leading to an increase in the number of cases of myopia. Those of you who have children, it might bear thinking about and having a look at their sleeping environment to make sure that they sleep in an environment which is sufficiently dark. It seems to be extremely important. Okay, so short sight, the image falls ahead of the retina, and the retina receives a blurred vision. In the other condition, also quite common, this is called far sight or hyperopia. In this instance, the eyeball is too short, and often the retina is too flat. And as a result, the sharp image is cast at the back, behind the retina. And again, if you attempt to look at things and have a sharp image, instead they see a blurred image. And again, this is corrected by lenses placed in front of the eye, either glasses or by contact lens. This far sight hyperopia is less common than myopia. Now this is one which almost every single human being ends up suffering from eventually. This is called presbyopia, and presbyopia is part of the aging process. You'll realize, if you're remembering the function of the lens, I told you that the lens has a natural spring to it, and its natural shape is more spherical. It is pulled flat by the ciliary muscles in order to focus the image on clearly on the retina. And so throughout your whole life, this lens is springing back and forth and back and forth and back and forth. And after a while, it starts to age. The proteins start to lose their elasticity. And by the age, usually around about 40, the lens loses its ability to rebound completely to its spherical shape. And it always remains a little bit flat. And it becomes very difficult to focus on some objects which are close by. Instead, you have to move them further and further and further away in order to form a clear image. This is the easiest of all of the disorders to correct, because all that you need to do, the lens that you place in front does not have to be one of the complex lenses that an optometrist will devise for you if you have myopia or farsightedness, hyperopia, but you can use a simple magnifying glass, and that is all that reading glasses are. Reading glasses are magnifying glasses, and they work perfectly well to bring the image to the retina itself. In actual fact, presbyopia ends up being like a sort of farsight, hyperopia, because it focuses the image behind the retina, not ahead of it, but behind the retina. But again, it is corrected quite easily just with a simple magnifying glass in reading glasses. Unfortunately, I have to tell you that most of you eventually are going to suffer from presbyopia. It's a little bit depressing when it happens, but it does indeed happen to virtually everybody eventually, that they have some degree of aging eyes, simply because the proteins in the lens start to age and lose their elasticity. Okay, the last one, it may again be familiar to many of you, and very often this condition is combined with one of the others, either myopia or hyperopia. And this is because arises because the shape of the cornea is not a perfect sphere. It should be almost perfectly spherical, but in some cases, the cornea is effectively slightly buckled. It doesn't have a perfect spherical shape. And this gives rise to the condition of astigmatism. And astigmatism results in multiple focal points. Instead of just forming a single image on the retina, instead some of the image falls behind, some of the image falls clearly ahead, and it gives rise to distortions in the shape that people are looking at. So again, astigmatism is very, very common, and some degree of astigmatism is probably inherent in virtually all lenses, in all corneas, but it's only when it becomes severe that it radically affects the image that people are seeing. And again, it can be corrected usually with the correct lenses. This is one of the ones it's difficult to correct with a contact lens. Can be done, but it's a bit more difficult to correct it with a contact lens. It's usually done with glass lenses of one sort or another. So that's the condition of the astigmatism. It's when the cornea is not perfectly spherical and instead casts multiple focal points instead of having all of the image in one plane on the back of the retina. It falls at different points ahead and behind the retina. Okay, so that's all we're going to talk about for the eye. Now let's talk about the ear. And the ear is an absolutely fascinating system. Our ears are in fact two distinct organs in a way. They both parts use a similar system, but they use the same system for entirely different purposes. So the ear is responsible, obviously, for our hearing. That's one. But our ear is also responsible for our sense of balance and posture. And it coordinates very, very strongly with the cerebellum to give us our sense of where we are in space and how we are moving in that space. And if ever you had a disorder of your ears, you'll know that any disorder of the inner ear can radically affect your balance and your sense of posture, of how you are standing. So let's have a look at the structure of the ear overall. First of all, there is an external ear. This part of the ear here is called the pinna, P-I-N-N-A, and it is structured to focus sound to this canal here, which is the external auditory canal. So this is your ear that you can shove your finger in. Lesson number one, don't shove your finger in your ear. In fact, specialists who work on the ear will tell you that you should never try and put anything smaller than your elbow into your ear. In other words, nothing should ever go into your ear. This is may sound counterintuitive because the sale of earbuds, for example, is enormous. People use a huge number of cotton earbuds to try and clean their ears. And when you try and do so, you actually can end up in a lot of trouble. And people do. The external auditory canal produces a wax. It's perfectly familiar to most of you, I'm sure. It is a brown, yellowy brown wax. This is a really distinctive color to it. It is produced most at the bottom of the ear canal, and it actually proceeds to be moved by production of more wax down the bottom. It moves like a tube slowly up towards the entrance of the ear here. And as it gets, under normal circumstances, as it does so, it dries, it becomes completely flaky, almost dust-like, and is easily shed from the ear. So that's the normal circumstances. As soon as you start fiddling with the system, as soon as you start trying to pour water in your ear, whoosh it around with an earbud, etc., so you mess with this little conveyor belt of wax. Now, the wax is there for a very good reason. That is, it's strongly antibacterial. And it keeps your ears free of infection by bacteria and by fungi as well. It's there for a very good reason. And under normal circumstances, the ear canal is not clogged with wax. In fact, the wax forms like a tubular shell around the ear canal. If you start messing with it and you start poking with cotton buds, etc., what inevitably happens is you start packing wax together with cotton fibers and everything else, and you end up plugging the ear canal up. And not only is that going to affect your hearing by literally plugging up the ear canal so that you can't hear, but it also encourages the growth of fungi and bacteria in the ear canal. Much better just leave your ears alone. If you have wax here at the very entrance that you can see or that you can feel, then you can clean that away, but do not go shoving things into your ear canal. At the end, there's another good reason not shoving things into your ear canal. At the end of the ear canal, there is a thin membrane called the tympanic membrane. It's very thin and it's quite fragile. And that's what we refer to as being the eardrum. And it literally is a drum. It vibrates as sound waves reach it. It vibrates just like a drum, the membrane on a drum. and that vibration is going to be communicated then to the inner ear. So that's the ear canal, wax at the end, the tympanic membrane. The next part of the ear is this part here, and it's called the middle ear. And the middle ear is filled with air, with gas, and it has three small bones. They are the malleus, the incus, and the stapes. And the in common parlance, the hammer there, the anvil, and the stirrup. And the stirrup there is the smallest bone in the human body. We'll see it again in a minute. There's three bones linked closely to one another. And the vibrations, the hammer, the malleus here, is attached to the tympanic membrane. When the eardrum vibrates with sound hitting it, the hammer vibrates and it transmits that vibration through all of these little bones to the stirrup bone there, to the stapes. And the stapes are attached to the next part of the ear, which is the inner ear. And we'll talk about this again in a minute. So this is the inner ear. There's a fine membrane there, thin membrane on the inner ear. There's a thin membrane there where the stirrup bone vibrates and communicates the vibrations to the inner ear. But I just want to tell you a couple of things about the rest of the middle ear. The middle ear is filled with gas, and there is a very fine canal which connects with your throat. And under normal circumstances, that is open, and there are a couple of reasons for that. The first is that this allows gas pressure to be regulated inside your middle ear. And under normal circumstances, this happens unconsciously. We continually clear the middle ear here to maintain the same atmospheric pressure that we have outside. Under some circumstances, if we undergo sudden pressure change, you can't do it quickly enough, and the eustachian tube kind of closes, and you actually have to do something conscious, like swallow or something. Some people, we can clear our ears, and what you're doing is you're actually opening this eustachian tube to allow the pressure to equalize. So, for example, you go up in an airplane. As you go up, the pressure around, the atmospheric pressure around you drops, but you maintain a high pressure inside the middle ear, and you compensate by swallowing or clearing your ears to equalize the pressure. Same if you're diving, you go scuba diving, whatever. As you dive down, the pressure increases. Same thing. You clear your ears to equalize the pressure. So that's the normal functioning. It's mostly just unconsciously we continually equalize our ears. There can arise situations where this eustachian tube actually becomes blocked. This is especially true in children who are subject to frequent throat infections and this sort of thing. And any inflammation of the throat runs the risk of blocking off the opening of the eustachian tube in the throat. And when that happens, various things. First of all, it becomes very difficult to clear the ear, and that itself can be uncomfortable. But once the eustachian tube is blocked, there's also a possibility of starting to build up bacterial infection inside the inner ear. The middle ear. The middle ear continually drains through the eustachian tube. Block the eustachian tube, and we run the risk of infections growing inside the middle ear. And this is very frequent in children, can happen in adults as well. If you have a bad cold or influenza or whatever, and you have an accompanying bacterial infection, you can in fact develop a bacterial infection here. And the classic symptom for that, of course, is earache. And earache can be agonizingly painful.
one of the reasons is that the pressure causes the eardrum to bulge. And in fact, if the fluids inside the middle ear build up sufficient pressure, then they can actually rupture the eardrum. So the usual treatment for this is to provide antibiotics, kind of quell the infection. But in addition, especially in children, the doctor may put in a small drain into the eardrum. It's completely painless, and it sits there for a while, and eventually the eardrum will actually heal. But you provide a drain to allow the pressure. If the eustachian tube is blocked, it allows the middle ear to drain and for pressure to be equalized. Okay, so let me just, I think it comes a bit later, what's happening. All right, so here's the stirrup, and the stirrup is attached here to this whole elaborate structure here, which is the inner ear. The inner ear is protected, very, very delicate, and it's very protected by a bony covering. It has this very intricate shape. There are two parts to it. The first we'll talk about is this here. It's called the cochlea. Cochlea means a shell, and that's because that's exactly what it looks like. You can see it's this curled structure here. And this is the part of the ear which is doing the hearing, which results in our ability to hear. The cochlea is a spiral. It begins actually here where the stirrup attaches to the bony shell at the thin membrane called the oval window. And there, we'll see in a minute that that leads to a canal which runs all the way around the cochlea and then back again down here. And then the sound wave is being transmitted through that canal, and the sound wave is then vented, it's voided into the eustachian tube. That is the other function of the middle ear and the eustachian tube, is to act as a sink for the sound wave as it leaves the cochlea. So it's, and we'll see its exact structure in a minute. The other part of the inner ear is this part here, which is the part which is responsible for our sense of balance. And this consists of three, they're called the semicircular canals. And you can see them here. There's one in one plane, one at right angles to it, and one in the other dimension at right angles to it. So we have a semicircular canal in each of the dimensions in which comprise our three-dimensional space that we are in. And it is these semicircular canals which are going to give us our sense of where we are in that space. And as we move, it is our semicircular canals that inform our brain exactly how we are moving and where we are in space as we are moving. The semicircular canals communicate with the rest of the brain through this nerve here. It's called the vestibular nerve. And the hearing part of the brain communicates with the brain, the hearing part of the ear rather, communicates with the brain through the cochlear nerve, which is this here. So there are two nerves associated with one another, which are going to communicate with the brain to link the inner ear to all of the analysis that is going to be done by the brain. For the moment, I think that's all we need there. So this, I don't need you to remember all the different parts, but I'm just want to point out something out to you, that a huge amount of our brain in humans is devoted to the task of hearing, understanding what we are hearing, speech, and understanding language. This is a very, very complicated process. And the senses of hearing
are intimately tied up with all of our sense of language and everything else. And you just, this is just an illustration for you. The main part that initially does analysis is in the temporal lobe. And here's the main auditory area. It's called the primary auditory area here. But there are associated with it many, many other parts of the brain. There is a part here called Broca's area. This is the part that we actually use to form speech. Broca's area allows us to make sound, know what sound we are making, and have intention of making that sound. Just making a sound is a very complicated thing because we can make many different sounds, and we do. We make many different sounds in order to speak, sing, whatever. This area here is called Wernicke's area. And this is the area that actually understands speech. Not only what we are hearing, but other people's speech as well. So it's our own speech we understand, and other people's speech. And that is governed by this area, Wernicke's area. These actually are also very closely associated with vision and with reading. When you read, there are areas of your hearing brain that are lit up. And not only that, all of these areas here communicate very strongly with the frontal lobes, because all of these things, hearing, reading, hearing in your brain what you are reading, all of these things carry emotional content. So they are also communicating with the limbic system and then with the frontal lobes as well. Hearing and speech and reading are intimately connected with one another, and they are extremely complex actions. And our ability to communicate by language in this complex manner, our ability to use abstract symbols and yet link those symbols to a sense of hearing and understanding is a very, very human characteristic. We don't actually see this in any of the other animals, even those which are very closely allied to us. It does not arise spontaneously. In some of the higher apes, it appears we can teach some of this. We can teach some aspects of this. So the basis for this lies in our evolution, but its final development seems to have occurred in human beings. At the moment, we are the only ones that do this to such a complex degree. And it's one of the things that make us very human. It is also one of the reasons why I am continually saying to you, those who read succeed. Because reading is such a complex undertaking. And when you read, and especially when you read and write, you are forcing information to many areas of your brain. And the more areas of your brain you can put information into, the more likely it is that you will remember it. Because when you want to remember something, you have to reconstruct. And you pull information from all sorts of areas of your brain in order to reconstruct a memory. And reading is one of the ways of developing that ability. Not only reading your textbook, but reading in general. When you read, you are in your brain constructing all of these things. You are hearing things, you are feeling things. All of these things are going on while you're reading, as well as when you're hearing things. Okay, so I would like you to remember, first of all, that the temporal lobe is the place where the first real analysis of hearing takes place, of what we are hearing takes place. Then remember the Broca's area is where we physically form speech, and Wernicke's area is where we actually understand, and all of these have to coordinate with one another. Okay, so let's think for a little bit about how we actually form that sense of hearing, of hearing a sound. Well, sound arrives through the ear canal. It also, by the way, arrives through the bone of our skull. A certain amount is communicated directly through the bones of the skull. But ultimately, the sound wave has to be transmitted to this inner part here called the cochlea. The cochlea is very complex in its structure. The initial transmission is by the three little bones, the malleus, the incus, and the stapes. The outside here is a thin bony shell. It is pierced by a membrane, a hole, and which is covered with a membrane. And that here is the oval window, which is attached to the stirrup. The stirrup vibrates in response to incoming sound. And it sets up a vibration inside a canal inside the cochlea. And that is transmitted throughout the cochlea. The cochlea is filled with fluid, a gel-like fluid. And it goes all the way around. And then, and it's in this first journey around the cochlea that hearing is accomplished. Then the sound wave leaves the cochlea and exits through the round window. The round window again has a membrane on it, and that membrane vibrates. And that voids the sound wave. Otherwise, if we didn't have it, it would carry on and on and on, echoing around the cochlea. And that's highly undesirable. We only want the sound wave to make one passage through the cochlea. And I'll just tell you right now that the hearing structures in the cochlea are structured so that you hear high-pitched sounds here at the beginning of the cochlea, and you hear low-pitched sounds down near the end of the cochlea. So as you age, and especially if you're exposed to high noise levels, this part here receives the highest energy wave formations, and this part here tends to wear out more quickly than the rest of the sound mechanisms in the rest of the cochlea, and we'll talk about that in a while. Okay, so here are the three little bones here put onto a dime so that you can see how small they are. That's the malleus, the hammer. That's the incus, the anvil, and this here is the stirrup bone there, smallest bone in the human body. And I'll show you an easier one to understand than this, but this is just to introduce you to the idea that inside the cochlea, for example, there are a series of canals running around. Those canals are separated from one another by membranes. And we're going to see that the cochlea is actually divided into three canals. The semicircular canals, which are responsible for balance, are somewhat differently structured. Here, they are tubes. And then at the base of, it is really semicircular, and at the base, there's a raised portion you can see here, which is called the ampulla there. So here you can see the semicircular canals there, and they're at right angles to it, and then at right angles in the other dimension. So we have a three-dimensional sense of movement from the semicircular canals. All right, so here we see how the sound wave moves. It moves through the fluid of the cochlea, and you'll see that this is the cochlea cut in across. And this is the receiving canal here. And most of the sound passes through this central subcanal. So this canal here is divided by membranes. The whole cochlea is divided here by quite a rigid membrane. So this whole canal there is where the sound is initially traveling through. And this initial canal is itself divided in two. In the center, there's the actual mechanism for hearing, which is called the organ of Corti. Corti being the person, I guess, who described it. The sound wave passes all the way around to the apex of the cochlea, and then it passes back down through this canal here, and then out through the round window. And there's no sound reception here. All the sound reception is in the first canal. And the sound reception is performed by a special, very, very specialized cells called the hair cells. The hair cells are highly modified epithelial cells. And they do literally have hairs on them. And those hairs vibrate. And that is how the perception is made. The hair cells, the hairs on them vibrate, cause the hair cells to interact with nerve cells and create a nerve impulse as they are stimulated by the sound wave. So as I told you, these hair cells down here at the beginning of the passage, those are receptive to very high-pitched sound, to highly energetic, high-pitched sound. Down at the end here, the hair cells are more receptive to low-pitched sounds. But there are two kinds of hair cells, I need to tell you. So just bear that in mind. I'll get to that in a minute. This is just another view of it. Here is the top canal here. The whole thing here is where the sound wave is initially passing through. And the most important part is this part of the canal here with the organ of Corti in it. Then the sound passes out through this canal down here. Okay, so here's this middle part, this wedge shape here. Here it is here. And the sound wave is passing through the fluids here, and it causes this membrane here to vibrate. These hair cells here are really bizarre because what they are amplifiers. As they're stimulated by the sound wave, they actually vibrate even more. The hairs on them actually vibrate, and they amplify the sound for these cells here, which are doing the actual hearing. So it's these inner hair cells here, which are doing the hearing. The outer hair cells here are actually amplifiers. By the time the sound wave reaches the inner ear, it may actually be very diminished. It's passed through it's passed through the membranes and the bones and the bone membranes and the fluid and everything. It may be very diminished. So it is amplified by the outer hair cells. When it's the outer hair cells just amplify whatever is coming through. If lots of inner hair cells are stimulated, we perceive the sound as being very loud. Okay. If only a few hair cells are stimulated, we perceive the sound as being soft. So just remember, there are the two kinds of hair cells, outer and the inner, and it's the inner that actually do the hearing and send a message off to the brain to tell your brain, yes, here is sound. Here's what they look like. This is a hair cell here. Don't worry about the cellular functioning. All I want you to know here, it's a very specialized kind of epithelial cell, and it has these hairs that project out of it. These hairs vibrate, and it is that vibration that causes the hair cell to produce the hair cell is excitatory. It can be excited to produce a nerve impulse, and the nerve impulse goes off and goes to the brain for analysis. Here are the hairs. This is this view from the side. But if you look at it from the front, here's the surface of the hair cell here. And you can see they're arranged in these beautiful arcs like that. and these are what are going to be vibrating. In the case of the outer hair cells, they actually move to amplify the sound. The inner hair cells, they vibrate and tell the brain that they send a message to the brain. The sound is being received, and that is then analyzed initially by the temporal lobe and then by all of the rest of the areas that we talked about before. Hair cells, all of the functioning of the ear, both hearing and balance, are due to hair cells. They have much the same structure in the semicircular canals. They just have an entirely different purpose in the semicircular canals. And they communicate, the hearing cells communicate via auditory nerves, via the cochlear nerve, which is an auditory nerve, to the brain. The semicircular canals communicate via the vestibular nerve, and they are going to communicate balance and movement, a sense of balance and a sense of movement. So here they are again. Here, these are the semicircular canals, again, shrouded in a thin, bony covering. The insides filled with fluid. And at the base of the semicircular canal there is a patch of hair cells. And the way in which this works, there's a slight swelling here where the hair cells are housed, and they form a little bunch of hair cells there called the cupula. This fluid in here can move. And as you move, the fluid actually stays in much the same place. You move around the fluid, and then the fluid impresses on the hair cells as the hair cells move, and that conveys a sense of movement. And the brain analyzes the information from all three semicircular canals of each ear, but then it also communicates between both ears. So, for example, I'll give you a very simple example of two ways in which this coordination takes place. First of all, as you're sitting at your desk, turn your head like that. And you must realize, as you turn your head, that set of semicircular canals is going in one direction. The other set of semicircular canals are going in the other direction. You don't have any sense of confusion in your feeling or in your balance. It's a perfectly normal movement, but you have a very strong sense of the movement. That sense of movement is actually being developed in your brain. It's being developed in those areas of the brain that are receiving this information. And that information is being communicated, especially to your cerebellum, in order to adjust your muscles so that you remain in correct orientation and that you keep your balance. Just think about something as complicated as walking. When you walk, walking is controlled falling. Each time you step forward, you're actually falling onto your leg, onto your feet. Your semicircular canals are responding to the most fine, exquisite movements. They respond to very, very small movements, and they allow all of the muscles of your body to coordinate just through this information that is being sent by these hair cells here in the semicircular canal. I give you another example of the activity and coordination of the semicircular canals. Stare ahead of you and keep your eyes fixed on something and move your head back and forth like that. Seems simple enough, right? Excepting, what did your eyeballs do? Did your eyeballs stay fixed and move with your head? You can do that, but you do it voluntarily. Okay, you can keep your eyeballs fixed, and they will move with your head. That in itself is really amazing. That your eyeballs just keep moving as you move your head. You're coordinating very complex muscles in your eyes with your semicircular canal information. when you were staring ahead and you kept your eyes fixed, your eye muscles had to compensate for the whole movement of your head. As your head moved, your head moves around your eyeballs. That information is all being conveyed to your brain and then to the muscles of your eyes through your semicircular canals. And it's all being conveyed because fluid is pressing on these hair cells at the base of the semicircular canal. That's marvelous. That's a wonderful thing. None of this is simple. It's all very, very complicated. Okay, so unfortunately, some degree of hearing loss is the price usually of age. And there are two kinds of hearing loss. The first is simple aging. The hair cells wear off. That is one of them. The nerves, the hair cells themselves become less and less and less acute. They lose those cilia. These can actually break off, and the hair cell loses its sensitivity. And as a result, we have a loss of hearing acuity in aging called presbycusis. Presbycusis, if you want to remember, I'm not going to ask you that, but if you want to talk about it at cocktail parties, then you can try and remember the name, presbycusis. That is normal hearing loss associated with aging. It can be very acute with aging. People can become profoundly deaf. But in addition, there is a genetic component, and tendency to deafness tends to be inherited. The second type of deafness, though, is in our modern age much more important, and that is we can become deaf due to exposure to loud or acute noise, acute, high intensity sound results in the loss of the hair cells in these cilia on the cells actually break off, and the hair cell becomes so damaged that it can no longer perceive sound. And two things can result from this. The first is just loss of hearing acuity. You just become deaf. You can't respond to sound anymore. But the other is that these hair cells, in response, they don't just go silent. Sometimes they become hyperactive and they start singing. They start producing a constant sound. And that is, you actually hear a constant sound, often a high-pitched whine in your ears. Other people describe it as like having cicadas stuck in your ear. And it is just constant. And this is a condition called tinnitus or tinnitus. I say tinnitus, but tinnitus is just as correct. And unfortunately, I have to tell you, there is a major epidemic of this kind of hearing loss in the modern times, and this is largely due to use of earphones to listen to music. Earphones project sound very, very powerfully into your ears, and in actual fact, it becomes your ears can compensate for loudness. There are ways in which the inner ear responds by reducing sensitivity to loudness, and our response is to turn the music up. And if you listen to music too loud through earphones, you're subjecting your ears to a very, very, very heavy burden. And unfortunately, tinnitus in young people is becoming more and more common, and along with it, profound deafness in some cases coming much earlier than it should. And the rule, if you're listening to earphones, if you're wearing headphones, especially buds that go into your ear, if other people can hear your music, you are going deaf. Your music is too loud. You're going deaf. You're actually damaging your ears. That is what the hearing specialists say. Okay, so we'll finish off there, and I'll see you again on Friday, sorry.